Hello and welcome to the second lecture on the calculus of variations. This lecture will be split into multiple parts, which will kind of cover some of the basic fundamentals on the mathematical theory of the variation of a functional. The whole idea is we'd like to extend many of the ideas from Calculus 1 and multivariable calculus, so finite dimensional calculus, to this theory of functionals. In order to do that, we first need to get a hold on what some of the exact mathematical spaces we'll be dealing with are, what the properties are of these spaces, as well as deal with some of the definitions of things like continuity of a functional and even the derivative of a functional with respect to its input functions. So far, we've discussed the concept of a functional, which is a function itself of some function space, or taking some function space into the real numbers R. Specifically, we've mapped it from a set S, which will then be taken, so it functions in the well-defined space S. It's a set of well-defined objects. These elements will be taken into the real numbers, and that's what gives us a functional. And so it's a very good question at this point to ask, what is this set S? What does it mean to say a set of well-defined elements or well-defined members? In the context of a functional, this means that it has to be some well-defined function space. Specifically, S is going to be a subset. So S is some subset of an actual linear vector space, which I'll denote as cursive S here, where this cursive S is a linear vector space of functions, sometimes just called a linear space. And so the reason that we're distinguishing here between the set S, capital S, and the set cursive S here is because the set cursive S is going to be satisfy all of the vector space axioms, meaning it'll be closed under addition of vectors, so vector addition and scalar multiplication, as well as satisfy all the other axioms. This S, capital S, is in general a subset of the cursive S, which means that all of the vectors in capital S have to be in curly S, but capital S does not have to be a closed set. And this is going to be very important to us because in general, sometimes we want to consider scenarios where the domain of our functional is not closed. For instance, once we start talking about the scenario where we consider variable endpoints, this subset of curly S is not going to be a closed subset of capital S. For example, if you consider the following set, the set S, where S is the set of continuous functions, so F in the set of all continuous functions on the interval from A to B, such that F is 0 at A, and F is L at B for some value L. For some interesting problem, right? This may be the set of functions that you want to maximize or minimize a functional over. However, this set S is not closed. So if you take this function, say F and G, two functions in this set, and you add them together, the result is not going to be in this set S, because at the boundary B, you'll end up getting L plus L or 2L. So this will not satisfy the conditions of being inside this set S. This is a typical issue in the calculus of variations, and it's going to be a very, very important issue for us to correctly define both the set of candidate maxima and minima, or that set for our possible location that we're searching for our maximum and minimum values of our functional, as well as it'll be important to define what's called the set of admissible variations. This is going to be related to exactly what form the variation of the functional is going to take. So to summarize this, essentially, in our calculus of variations problem, in general, we'll be trying to minimize or maximize or solve for critical points of a functional and be deriving necessary conditions for doing such a thing. And we'll be searching through some set S, which is a set of competing candidate functions. In general, this is not a vector space, as shown in this previous example, but it is a subset of some vector space of functions. Whereas there will be some other set we call curly H, which is cursive H, which will be a set of admissible variations. And this actually is not a set, but it should be a vector space in general, because we want to be able to add variations together to be in the actual space itself. So a vector space over a field F is a set S, cursive S, that is equipped with two basic binary operations. These operations are vector addition and scalar multiplication that satisfy the following axioms. So I'll list the axioms in a second, but I want to note here that, or just remind you that a vector space is also sometimes called a linear space, and the field, sometimes called the field of scalars, is typically taken to be the real numbers or the complex numbers. However, you can take any field use any field you want to define a specific vector space. So I've written down all the axioms right now, and I'll go through and explain these, but they should be familiar to anyone who's seen the definition of a vector space in, say, a linear algebra course. The first two properties that need to be talked about is the closure under these two binary operations. So a proper vector space is closed under the addition operation and the scalar multiplication operation. And what that means is this binary operation essentially takes two input elements and gives a new element that lies inside the original space. So we call this operation x plus y for addition. This should be defined, and the result of an addition should be inside the original space. And same thing with the scalar multiplication. For any, these properties are going to hold for any values of x, y, z in the vector space, and any scalars, alpha, beta, and gamma in the field F. The next property is associativity, which means that for addition, it's standard associativity, meaning that if you take the element x plus y and then add z to it, the result should be the same thing as taking the element x and adding the element y plus z to that. This is just associativity of vector addition that needs to be satisfied. And we also have something that's similar to associativity for scalar multiplication. It's not the same thing as the associativity property from before, but it's very, very similar. It basically says that if we scale the vector x by beta, so we multiply by the scalar beta, and then multiply by the scalar alpha, so we multiply this resulting vector beta x by alpha, we should get the same thing as first doing the multiplication of alpha with beta, the two scalars alpha and beta, and then scaling the vector x by whatever this quantity is. So these are two properties that need to hold in any vector space. The next one is commutativity of addition, which is that x plus y equals y plus x for vector addition. We must have the existence of certain elements. For instance, we need an additive identity, so there exists some element in the vector space S such that the vector addition of this element with any other vector will just yield the original vector itself. So this is sometimes called the zero vector in the set S, but this thing has to exist, has to be inside of our S. And same thing for multiplication. We need some element in our field, which we typically call the multiplicative identity, which that if we take this element in this field, typically noted as 1, if we do the scalar multiplication of any vector in our vector space S with this 1, we recapture the original vector itself, X. And we finally, for the existence, we need to have the existence of an inverse vector for any input vector X. And what I mean by inverse here is a additive inverse. So there should exist a y in S such that x plus y equals 0, where y is called negative x. You put a negative sign next to x. And this is just that saying that there, for any value x, any vector x, you can find a vector negative x, such that when you add the two things together, you recapture the additive identity. And finally, any vector space needs to satisfy distributivity, both with respect to the scalar multiplication and with respect to the vector addition. So what I mean by this is that if you try to scale a vector x by the sum of two separate scalars, so alpha plus beta times x, this needs to be the same thing as alpha times x plus beta times x. And likewise, if you try to scale the vector x plus y by alpha, this needs to be the same thing as alpha times x plus alpha times y. So these are the fundamental axioms that define a vector space, and it turns out that these are very, very important because essentially they tell us what sets are vector spaces and what sets are not vector spaces. And most of the sets of interest, and certainly all of the sets of interest for us, are going to rely heavily on being a vector space. So what I'd like to do now is get started talking about some examples of vector spaces. And many of these you'll hopefully be familiar with from other classes in mathematics. The first one being when you take the set to be the set of vectors of real numbers. This is elements of the form x equal to just a vector x1, x2, all the way to xn, where these elements xi are real numbers. In 3D, this is R3. So if n equals 3, you have 3 separate coordinate axes, one for x1, one for x2, one for x3, and you can draw out vectors geometrically as being arrows going out to each individual coordinate. But it's fairly straightforward, I think, to go through and verify that this is a vector space. And it's one of the most important vector spaces in multivariable calculus, because you're considering functions from this vector space to R in multivariable calculus. The underlying field in this example being the field of real numbers. So this is where we're pulling our scalars from in this example. Another example, very good example, is the vector space of complex valued vectors, CP. So this is the space consisting of vectors of complex numbers. So anything in this space will be of the form Z1, Z2, it's a vector, all the way up to ZP, where each one of these elements is a complex number. So every one of the the components in a vector in CP is of the form a.k.a. plus bk times I. The elements of this vector Z are just complex numbers. And it's interesting to note here that in some sense this set CP is isomorphic to a specific real vector space, but the underlying field in this scenario is the field of complex numbers, whereas the underlying field in this example is the field of real numbers. Not only that, but this CP is isomorphic to a specific n-dimensional vector space, specifically because for each one of these complex numbers, you have two real numbers that are needed to define it. This vector space CP is actually isomorphic to R to the 2p, where n is 2p. The final finite dimensional example that I want to talk about is actually a function space, but it's a very special function space. It's the space of polynomials. So if you take the set of polynomials, so the set of functions from R into R, such that P of x is equal to an times xn plus an minus 1, x to the n minus 1, and so forth, all the way down to a1x plus a naught. This is a set of polynomials, and specifically we'll take the coefficients in R, so you sometimes call this Pn of R. This is just the space of nth degree polynomials. And this space is going to have dimension n plus 1. Because each of the polynomials is uniquely determined by its coefficients. And since there are n plus 1 coefficients for a polynomial that has degree n, this is a vector space that is isomorphic to our n plus 1. Next, I'd like to move to some examples of an infinite dimensional vector space. The first example that I'll talk about is of the space L, lowercase l, of some field f. I'll just use the field R for simplicity. L of R is the space of infinite sequences or functions from the natural numbers into the field, underlying field. So a vector in this space is sometimes called a sequence. So a sequence an, which is an ordered list of infinitely many values from your underlying fields. In this case, a1, a2, all the way up to infinity. Such an object we call an infinite sequence, and in, say, Calculus 3, you typically see infinite sequences, and you learn about convergence properties of infinite sequences of real numbers. But it's important to point out that we could consider infinite sequences of complex numbers, or really any other well-defined mathematical object. And for my final few examples, I'm going to write down a couple different examples that are going to be of particular interest for us in this course. So the first example being C0 on an interval from a to b. And this is simply put the set of all continuous functions where the definition of a continuous function can be taken exactly from either your Calculus 1 class or your Introduction to Mathematical Analysis class. The space C1 of AB, which is the set of all continuously differentiable functions. And these are functions on the interval from a to b and r that have continuous derivative. In fact, more generally, we can say the set ck on the interval from a to b, where ck is the set of all continuously differentiable I guess I should say kth continuously differentiable functions. And this is the set of all functions that have a continuous kth derivative. And recall from your Calculus 1 class that if a function is differentiable on a closed and bounded interval, that function necessarily has to be continuous on that interval as well. So we actually have a very interesting inclusion here because the set C1 is in fact a subset of the set of all continuously differentiable functions. So it's a subset of C0, and likewise so for all of the other CK functions, set of functions as well. This is going to be an important point when we distinguish between what's called a weak minima and a strong minima of a functional. Additionally, we can define generalizations of these sets because we anticipate that for certain problems, the problem might be solved in not the set of continuous functions, but the set of all sectionally continuous functions. So this is the set of all functions that are continuous on subintervals of the interval from a to b. So we might talk about, say, CS of AB, which is the set of all sectionally continuous functions. And a function is called sectionally continuous if it has at most finitely many jump discontinuities. It's relatively straightforward to verify that this is in fact a linear vector space, just like these three are as well. We can also define the set CSK, which is the set of all sectionally k differentiable functions, which has exactly the same meaning as before, that for a function in this set, the function's kth derivative has at most finitely many jump discontinuities. And in addition to these two sets, which will be very important for certain problems, we can also even specify certain discontinuities. So for instance, if you want to specify, say, that a function has discontinuities in set P, where P is x1 to xn, maybe it has n finitely many jump discontinuities, you can define the set CSPK on the interval from a to b which is the set of all functions in CS or CKS. So functions that have at most finitely many, whose kth derivative has at most finitely many discontinuities, jump discontinuities, but specifically at the points x1 to xn. So you can see that these sets are they're subsets of the previously defined sets. All of these vector spaces are very useful and will be extremely useful in the calculus of variations. Mainly because these are all examples of sets of competing candidate functions for which we might want to try to maximize or minimize a functional.